Okay, so in today's video, we're going to go over a general setup of the UVSD software that we use for software development, as well as general functionality of using the GIO LEDs that are within the dev board itself. So all of these tutorials presuppose you've already downloaded and set up both HalCoGen and CCS. If not, take a look at our GitLab, which is git.uvsd.ca. And if you take a look in there, you will notice that within our Getting Started list, we have links and recommendations with both the settings and the programs themselves that we'd like you to download to use for software development within our club. So, provided that that has been done, we're going to get started here on a basic project that is essentially going to flash those little LEDs that are within your development board. So, if we look at the schematics here, you'll notice there are two very small lights right here. Hopefully you're looking at a board yourself right now, and you'll notice there is one right there and one right there, and they're just tiny little LEDs that are accessed via the GIO protocol. So what we're going to do to start is we're going to get set up in HalCoGen. So for your awareness, the standard procedure with UVSD software is we first create what is known as the abstraction layer within HalCoGen, and then we're going to utilize a software known as Code Composer Studio, and what you're looking at right now is a project that was already being worked on. And within Code Composer Studio is where we do the actual coding, but we're going to start with HalCoGen today. So what HalCoGen does essentially is creates a nice predefined interface between user code and the actual board itself. So if you've taken a lower level programming course, you know how much of a pain it is to communicate with a processor directly. So the nice thing with HalCoGen is what it does essentially is you give it a general framework. So you tell it, you know, this is the chip we're using, or this is the development board we're using, and it knows how to set up all the general interfacing properties. So for instance, how you would access the I2C registers, which is a protocol, or how to pull the GIO pins or something along those lines. So they essentially do all the hard work for you ahead of time, which you'll see in a second. So that's what we're going to start off with today. So we're going to go to File, New, Project, because we're just creating a new project, and what you're going to see here is a list of all the potential processors that are supported in this version of HalCoGen. So in your case, you're likely to be using the TMS 570 LS12, which is our standard development chip. So what you'll see then is a bunch of sub-iterations of the same chip, as TI makes just a whole ton of chips. For this case, we're using the 570 1224. If you're not sure of what you're using, or you're using something different, just take a look at the chip, the microchip that's on the board itself. It will list this this name. So next thing you're going to do here is you're going to select a project name. So this is just the general, or the project overall name that you're going to use as a directory to store all the files, things like that. So for my purposes, I'm going to call it video project. In your case, maybe you want to call it test project 1, something along those lines. Doesn't really matter. The only recommendation I have is to use something that's easily typable and memorable, because both HalCoGen and CCS are very picky about the paths that they use. So if you mistype where to find something along those lines, a lot of things will break, and it's going to be a real headache to fix. The other thing you're going to want to do here is set up a location. So the location essentially is a top level directory. So it's where you would store all of your UVSD projects. So if you look in here in this browser, you'll notice that in my stuff, I have a whole bunch of sub projects that I've been working on. So if you haven't pre-established a folder for that, I'd recommend you do that. Put it wherever you'd like, call it UVSD or EcoSat, something on those lines. It's just your top level directory for all your projects. Keep the create directory for project checked, as that's essentially going to create this sub project as a new directory underneath the overall umbrella of your UVSD folder. So I'm going to click OK. I'm just going to get a pop-up that asks if I indeed do want to create the new folder, which we do, so don't worry about that. Okay, so what HalCoGen is going to generate now is a GUI that represents the abstraction layer communicating with your chip. So there's a pretty overwhelming amount of information here, but what's really great with the processes that we use here is that most steps, for at least for beginners, are accomplished in three or fewer steps, which is great. So we're just going to go through how to kind of sift through all this information to get what you really need. So again, the goal of this project for today is we're going to be flashing those LEDs within those boards. Now, those LEDs use the GIO registers within your chip. So what GIO is it's essentially a single bit information protocol. which if you've taken, again, a lower level programming course, you know that a single bit grants you the possibility of either a 0 or a 1. So in that case, that typically translates to meaning on or off. So GIO obviously is not super great for information transfer. However, it is nice for doing things like turning things on and off, which is what we're going to use it for today, as we're going to be flashing those little LEDs. So if we go back to look at the board for a second here, what we're going to see is, and I don't know if I can actually get it on this screen, but if you're looking at this exact same thing here, what you're going to see is this says LEDB, and you're going to get a number somewhere in that range. Again, I can't particularly see it because of the low resolution, but what it's likely to be is LEDB1 and LEDB2. LEDB2. So essentially what those are the port designation and then the specific bit within that that port. And I should be saying register, actually. So the development board you're looking at right now has 2 GIO registers, meaning that there's eight different bits to work with. In this case, those 2 internal LEDs utilize the B register, and it utilizes bits 1 and 2. So that means if we ever want to directly access them, and for whatever means, we need to go to port B and we need to access either 1 or 2. So now if we go back to HalCoGen, after looking at the board, we can now determine essentially what we need to change to start to access those things. So as I mentioned earlier, there's kind of a 3-step process to polling any sort of pin or using information on the board. The first is enabling the driver for the specific protocol. So typically that's done already if it's a more common one, but it never hurts to look. The next thing is to set up your pin mux, which I will explain a little later in the SCI to UART protocol, as that actually requires pin mux. Sometimes it does, sometimes it doesn't. The difference with that is pin mux will affect external sensors, so things that are plugging in to those little headers that you're seeing up here, so things that are externally connected to this, whereas internal things do not utilize the pin mux function. And then the last thing you're going to want it to do is go into the specific protocol itself, and there's likely to be changes to the settings you need to make in there. So there's kind of 3 steps. So again, there's enabling the driver, changing the pin mux if applicable. If it's an external sensor, you might need to do that, and changing the settings within the specific protocol. Again, all 3 of those are potentially optional. It varies from setting to setting. So today we're going to kind of go through why those vary and why those are potentially optional, and for this specific example, why we do need to change a few things. So we're going to start with our driver enable. Now we go into driver enable, and for GIO it's extremely simple. So there's just a single GIO driver. We just want to check that that's enabled. It is, so that's great. That means we can use GIO on this chip. Next thing we're going to want to do is we're going to go head over to GIO. Now you'll notice I did skip over pin mux. Again, that is because pin mux directly affects the header pins. Those are changes that happen to those. Because this LED is strictly internal, you just have a data bus inside of the board itself. There's nothing going externally. There's no need to change any pin mux in this case. So if you recall from earlier, what we need to affect to be able to essentially access those 2 LEDs are GIO port B, which we can see here, bits 1 and 2. Which you'll notice right down here. So again, there's a bit of an overwhelming amount of information. What's great for us is there's only one specific thing you need to change here, which is the DIR checkbox. So what I'm doing when I'm checking this checkbox is I'm saying we want to, as you can see in the pop-up there, is we want to enable the output direction for port B bit 1. So what that's saying is, because GIO can obviously take in information or pass out information, in this case we're saying we're firing information to that GIO pin. So we're wanting it to be an output because we're flashing LEDs. So I'm going to enable both 1 and 2 so we can output to both LED 1 and LED 2. Now that's the extent of the changes we're going to be making in HalCoGen for this specific project, because we've just set up the GIO pins that are internal to the board. So what we're going to do next is we're going to Control S to save. And then what we're going to do is we're going to go drop down here. And actually before we do that, I'm just going to go into my File Explorer, and I'm going to show you what the current state of the project looks like, which you can do as well. So if I navigate to my EcoSat, my stuff, and then it was video project, you'll notice right now we just have 2 files, a DIL and an HCG, the HCG being the HalCoGen project. So right now it's very bare bones, but what you'll notice is when we go back to file, and we're going to click on the button generate code, what's going to happen is you'll see a lot of activity down here in the output. You go back to our file explorer, and we're going to see all of a sudden there's a lot of things that have been populated. We use C, by the way. I probably should have mentioned that earlier. But C is the language of choice for when we use the free RTOS kernel, which is our operating system kernel. Again, all of these things are documented online. Obviously, we're available for questions as well. So those are both potentials. But just for your awareness, we are using C for this. But you'll notice right now, after I click generate code, what's happened is we have a whole ton of things in here. These are essentially the as I mentioned before, the abstraction layer, the framework that we're going to use to communicate with the board. So if you're aware at all of protocols or pins, you're going to see there's a whole lot of acronyms in here that have to do with different communications protocols. So this one's of particular interest to us, right? It's GIO.C. So essentially, it's just established the code that we need to communicate to the board to use GIO. So rather than having to code all of this stuff on our own by hand, it's essentially established all of our framework to do that ahead of time. So that's a huge time saver. So what we're going to do now that we've finished up with our HalCoGen work is we're going to head over to Code Composer Studio. So Code Composer Studio is just an IDE. It's not required for usage in development because obviously you can just use a notepad or something on those lines. But it's extremely, extremely helpful to use it because it has an internal debugging GUI as well as an internal terminal that we can use to pass. We can read the information that the board is sending to the computer back in a much more clean and easy fashion. So highly recommend you do use this at least to start, and then perhaps when you get more comfortable you should move on. So Code Composer Studio again is now what we're going to do is we're bringing that pre-generated framework that was created by HalCoGen into an IDE, so now we can actually mess around with it, personalize it, make it our own. So setting up the CCS project is a little more complicated than it may seem, largely because of the path issues. So this is where I do highly advise you're very careful with what you're typing because paths are going to be a huge pain. So what we're going to start with is we are going to What we're going to do to start is we're going to go and we're going to leave the target blank. The issue right now, for those wondering, is I'm recording this without an actual board plugged in, so sometimes things won't pop up because it's not automatically detecting that board, but things are looking fine. So leave this blank. What you're going to do now is you're going to go over here. You're going to see, obviously, again, a large number of chips, which you would have also seen in HalCoGen. Again, select the same one that you used in HalCoGen, so the LS1224. The next thing we're going to use or change is the connection itself. So you're going to want to change this to the Texas Instruments XDS 110 debug probe. So essentially what a debugger does is it's the converter between the code we have on our computer to the code that the chip understands. So there's different ways of doing this. There's a bunch of different debuggers. In this case, the debugger we are using for our project, so it's within the development board, as well as the external debugger that we use to connect to the OBC, which you'll see a little later on as you gain experience with the club. This probe is what we use to debug, so you're going to set it to the XDS 110. Now, for the project name itself, again, we're going to want to mimic word for word, or letter for letter, I should be saying, the name of the last project that we generated in HalCoGen. So again, just so paths don't get messed up, we want those to be the same. You're going to uncheck default location because it does need to find it in that new folder you made, unless you set that to your default location initially. Either way, it's possible to just confirm that it's working well and connected. So what we're going to do here is we're going to go into the My Stuff, which for me is my top level folder, and I'm going to go and click on Video Projects. So you're not going to click on the includer source because we don't want it to go within the project itself. We just want it to be on that top level of this individual project. So we're going to click OK. Compiler version, leave it as whatever TI has given you. For me, it's 16.94. And then the last thing we're going to do here is we're going to take a look at our options for how it generates the project. Now, your default and the default it sets and what you'd probably expect is we're going to use main.c. However, we do not want to use that because when we generated the code initially, within source itself, it generated a main.c for us already called sys. Or if you're using the 43 board, it'll be HL_sys. But it'll generate a main.c function already set up for you. So we don't actually want it to create one. So we're just going to go flat out empty project. Now we're going to finish, and what you'll notice is over on the left-hand side here in the Project Explorer, it's just added it. So pretty straightforward. It's just added the project so it's accessible within Code Composer Studio. No big issues, so we're nice and ready to go. So what we're going to do now is we're going to go within the source code. So again, those are the .c files, the ones that are actually executed, not referenced. And we're going to go to sys.main. So this is, as I'm sure you know, main is always the starting entry point for a program when it runs. So main is where we're going to start all our code. For purposes of this demonstration, we're going to be writing all of our code within main. However, for writing both flight code and testing code, you want to write things more modularly, meaning that we have a lot of things, a lot of functionality to fit within our code. So we're going to be writing a lot of separate .c files and header files and things like that. So main is likely just to become an entry point and that's it, and then it'll send off to something else. But for purposes of this, we're going to leave everything within main because it's a fairly simple task we're doing today. So now this is probably looking a little more familiar to you if you're not already familiar with FreeRTOS sort of development. This is just a main function. A lot of comments, things like that, but all we really care about here are our hash includes, and it's given us a main function, as you can see here. So here's our baseline framework, totally bare bones, completely empty code that we can now put our own information in to start working. So with the task at hand today, which is flashing the GIO, what we're going to need to utilize are a few of the built-in FreeRTOS functions. Because again, that's what HalCoGen does so well, and why we use FreeRTOS is all these complex tasks of, you know, polling a specific pin or getting information from a specific pin or something like that are already somewhat done. Obviously, we need to figure out where we want to put that information and what we want to do with it. However, the process of actually gathering the information has already been established within our framework. So what we're going to start off with is we're going to start with some includes. And what I'm going to note ahead of time is you're going to notice they really hold your hand with a lot of these this code here. So we have user code begin 0, user code begin 1, 2, 3, so on and so forth. When I first started, I had a tendency just to delete those and write my own stuff because it felt unnecessary. However, there is a purpose to that. And what the purpose is to these user code begin end sections, so if I were to type in here, is that these sections are essentially untouchable by HalCoGen. So what I mean by that is, let's say we have, and we're going to do this actually, is let's say you've gone to HalCoGen and you've only set up GIO because at the time you thought that's all you needed. So you've written your CCS project, a whole lot of hard work has gone into that, and you click save and build and everything's great. However, you realize, oh no, I want to add in I2C protocol functionality, something along those lines. So what do? Do you copy over the project to a brand new one? You know, there's it's a real pain to work with that, so on and so forth. Now, the great thing with HalCoGen and CCS is that you can actually go back to HalCoGen now, take a look at this project. It's preloaded for us because I was just working on it. If not, you can just go into File, Open up the project. And you can actually make more changes and go and regenerate the code. And what it's going to do then in the background is all those .c and .h files that are generated, it's going to regenerate them in your new configuration. Now, obviously, it needs to wipe the directory and regenerate it. But by typing code within these boundaries, it's not going to touch the stuff that you've written in here. So essentially, you can totally rewrite the abstraction layer and leave your the code that you've actually worked to personalize it totally untouched. So you can make whatever changes you want in real time. So the standard for us is we're going to put global variables, things like that, in our 0, and for 1 we use hash include. Or we place hash include. So let's start with the hash includes we're going to need for this. So one of the ones we're going to need is hash include FreeRTOS.h. That's just going to include the real-time operating system functionality. And then what I'm going to do here is I've already written a program because obviously I can't remember all the header files and things you're going to need ahead of time. So this is essentially where we're going to end up here. So I'm just going to copy over a few of the ones we're going to need for now. Another one we're going to need for now is hash include standard input output, which is hopefully something you're familiar with already. We're going to include GIO, which obviously is for purposes of utilizing GIO within our function, which is what we're going to use to flash those LEDs. We've already included FreeRTOS. And these ones, operating system task queue timer, we don't need because we're not actually writing an operating system right now. We're just writing a basic function. We'll get into operating system code in the third video of this series. And the last thing we're going to include is #include syscommon.h. Now, for a sanity check, what we're going to do here is we're going to save and build and just see if anything is broken to start, because the worst thing you can do is write a whole ton of code and then build and then have a million errors that you got to deal with. So I'm going to click build here, and what you're going to notice actually is it's going to be broken right off the bat because there's something I forgot to do. So just to give you guys a general familiarity with Code Composer Studio itself, obviously we have our project explorer here, the different projects we're working on here, and then down here we have kind of a console thing. So you have a terminal, which we'll be using later to read information, advice, which you don't really need to use. Typically the TI forums are the best place to find advice, and problems, which is essentially just a list of the different errors you get. So fortunately, much like Java, Code Composer Studio has a tendency to kind of hold your hand in terms of giving you a lot of information about the errors you're getting. However, all that information can be a little overwhelming. So this is a very, very common issue people have to start off with, and it's just a dumb little mistake that most people make. And that is forgetting to set your path up properly. So you'll notice right off the bat, and this should be a dead giveaway, is I'm getting a whole ton of errors that say can't find all these header files. Now the reason is most likely because of the fact that it doesn't know where to look in the first place. And you'll notice there's a whole bunch of errors after. Again, as standard programming practice, you should be starting with the top error you see and working your way down, because oftentimes if you fix the top one, you're going to be dealing with a lot of the stuff underneath. And as you can tell based off of these indicators, clearly there's a path issue. So what I forgot to do here is to go into projects and actually set where the include files are. So if you recall, when I went to File, New, CCS Project, I connected this project, or I should say I inserted this project into that top level project that we're looking at here. So I inserted into this video project. However, I didn't directly tell it which file is used for the include. So CCS doesn't like to make any assumptions. It's fairly dumb with finding where specific things are. So it's not really willing to go within files to look for things. So we actually have to set the specific includes file. So we're going to go to Project, Properties, and then we're going to go, you likely have to expand this dropdown, Build. We're going to go to Include Options. So essentially this is just, we're going to set where Code Composer Studio for this specific project. Just for the record, this does not mean for every project. This is just for this one alone, where it's going to look for those header files. So we're going to go to Add. And what we're going to do here is you want to avoid using browse, because what browse does is it sets a static link. So what that means is it's going to give an actually I can just show you, is what it's going to do is it's going to create a reference to the header files in a non-flexible manner. So what I mean by that is you'll notice when I do this, it's just a straight up link. So go to C, go to Ecosat, my stuff, so on and so forth. The reason we don't want that is because if you end up moving your project at all, it's not going to be flexible in terms of knowing where to reallocate that pointer. So what we want to do instead is we're going to go to Workspace, we're going to go to Video Project, and we're going to go to Include. So it's, as you can tell, it's the exact same location. However, what we've done now is we've created a dynamic link. So if we end up changing where this workspace is located, since it's just referencing a variable that points to this location, it's going to move with it. So it's a lot more flexible. So I'm going to click OK. And now that header files location has been added, CCS should know where to look for it. So I'm going to click Build again. And there we go. Within problems, we have none. So that solved all those issues. Obviously, 70 looks pretty overwhelming, but one simple fix solved all of that. Okay, so now we've established kind of the framework within CCS itself for what we're going to do. So now we're going to actually write some code within main. So what I'm going to do is I'm going to actually just click and drag this code that is pre-established over to our main, and I'm going to go through step by step what it means. So again, there's a lot of predefined functions within our code because things have been done for us already for good reason. It saves us a lot of time. However, obviously it's important to understand what each of these functions mean so you know how to use them correctly. So let's just go step by step through what this main does. So the first thing we do here is GIO init. So what that means is it's telling the whatever's reading the program, it's saying, okay, let's initialize GIO. So now GIO is active. It's something you can actively pull. You can use it, so on and so forth. So this is, again, just one of those standard programming conventions you're going to have to get used to typing. So if you wanted to use the SCI, no, SCI is a pin, but still, yeah, if you wanted to use SCI, you would just use SCI in it. If you wanted to use I2C, you'd use I2C in it, so on and so forth. It's just a standard programming practice that you need to use. So when you're running the program, it knows, okay, we're going to use GIO. Next thing I'm going to do here is I'm going to create just an infinite while loop. The reason I'm doing that for today is because we're not actually creating an operating system scheduler. All we're doing is we want this just to run over and over and over until we unplug the board, just for purposes of today. In future use, we want to avoid infinite loops for good reason, as obviously if everything's in an infinite loop, we can't react to anything in any sort of time. However, for this case, since we're just flashing lights, it's totally fine. So within this infinite for loop, I've placed the code that is essentially flashing these lights. So it's a fairly simple program. However, you're going to notice there's a lot of things that you might not recognize right off the bat. So the first thing is GIO set bit. So GIO set bit essentially says go to a specific bit and then change it to whatever number you want to set it to. So you'll notice the great thing is when you do a predefined function like this in CCS, it will actually tell you in this little pop-up here what exactly it is doing. Because it's low-level code, it can be a little hard to understand. So if you look up the free RTOS documentation, which again is on our GitLab, you can actually read into the actual implementation in more English words. Another valuable resource are your actual header and source files itself that were generated by HalCoGen, as those are the implementations of all of these functions that are pre-established. So that means that if you go in there and take a look at what they're doing, you'll know exactly what's going on under the hood. So as you can see, it may be a little confusing to look at, so I'll just highlight this one. There are three major parameters. You have a parameter there, and a parameter there. So pretty straightforward. Parameter one is the port itself you're using for GIO. So as you recall, it's GIO port B. The second is the bit you're using. So GIO port B bit 1. So that should be the top LED for you if you're looking at your 12 board. If you're looking at a 43, I believe it's GIO port A 0 and 1, something along those lines. It might be 7 and 8. Just use whatever number corresponds with the bit you're trying to access. And the last thing we're doing here is the actual set value. So obviously our options here are either 1 or 0. Now we haven't hard-coded a 1 or 0 because we want it to be changing back and forth. So what's happening here is we have a little bit of math going on that's saying, okay, read the current state and change it to whatever the opposite state is. So there's a nested function in here, as you can see, and it's GIO get bit. So again, pretty straightforward function. All this is doing is it's saying go to this specific bit, so port B1, because obviously that's the one we're trying to impact. And it's saying, okay, get that value. So let's say it's 1. Then what we're going to do is we're going to XOR XOR. So if you've done a lower level programming course, you know what this is. We're going to XOR it with 1. What XORing it is with 1 is it's always going to change it to the opposite value. If you don't believe me, just write it out on some paper, test it out, or look it up online, something on those lines. So XORing something with 1 essentially just flips it. So if GIO get bit was 0, then it's going to XOR it with 1 and it's going to become 1, so on and so forth. So essentially this is just the function that switches it to the opposite state. Then what I've done here, because again we don't have a scheduler implemented, so we're literally just wanting to kill time, is I've written a very large for loop. This is actually a little too large. I believe this is going to be roughly 10 seconds. So I would do roughly, what is that, 1 million? Yeah, roughly 1 million, something like that. Just mess around with the number in your programming, and obviously this is going to change how fast the light is flashing. The purpose of this is to delay your processor with a bunch of NOPs, or no operations. that are going to waste your processor's time, so that way you can visibly see the light flashing. Because if I didn't have this, your bit would be being set at a very, very, very fast rate that's likely difficult, if not impossible, to see. So this is just a delay. So obviously it's going to set the bit to the opposite, delay within this function here, and then go back to our while loop and do it all again until you power off the board, essentially. So that's the extent of the code for today. Again, very straightforward. With this, now what you're going to want to do is you're going to want to save. You're going to want to build. And hopefully we don't run into any issues here. We have a couple warnings. What are they? Statement is unreachable. Now this isn't a problem, and this is very common, is obviously this return is not reachable because we have an infinite loop. So we're going to ignore that. And then what you're going to do is you're going to press this little debug button up here. Now, today what you're going to be seeing is I'm going to get probably a large amount of errors or just it not working because I don't have a board plugged in. However, provided you have plugged in your board via USB, it's just as simple now as pressing debug. And again, it's not going to find that XDS debugger. So this isn't going to work, as you see, but if your board is plugged in, you'll be just fine. And what you're going to notice, and I'm going to keep it in the debug interface just quickly here, is what will happen most likely is your LED will flash once and that's it. What you want to do then is you're going to notice that once this is finished debugging and it's running in quotation marks, what you're going to want to do is press the play button up here, and that's actually going to get the code to start running, and you should see a nice flashing light on your LED. So that's going to conclude our basic setup and usage of GIO LEDs within your board itself. This does extend as well to the GIO header pins that are on the board, so if you wanted to connect an external one, it's roughly the same process. We will be going over that probably in person with you in the future, but you'll see an example very similar to that in the next video, which is SCI to UART communications, which is essentially how we read and send information to the board itself.